So if we have 1/2 times v, it's literally just vector v cut in half. So 1/2 vector v is just vector v, but half of it. That's probably a little more than half, so I'll make this a little bit longer. Close enough. So if you have 2 times vector v, it just doubles the v vector. But it has the same direction, same magnitude, but it's just doubled in length, or magnitude as they call it. Now, if you multiply it by a negative, it just changes direction. So let's say, kind of separate that a little bit. If that's our vector v, if you want to find negative v, negative vector v, that's just -1 times vector v. So if our v vector, actually I'll write our v vector as dotted. So let's say this is our vector v. Then negative v is the exact same length but in the other direction. Okay, so any questions on that one? All right, I'll leave that up there. So far, all of our vectors have started at the origin. But in some cases, you have all of those equivalent vectors that move all over the place. You can actually figure out what the vector is by the terminal and initial point, even if it's not at the origin. Okay, so not all line segments have an initial point. At the origin. Okay, so in order to find the position vector v, that's our v vector of a line segment that is not at the origin. I mean, you could use it for at the origin, but you don't have to when it's at the origin. Okay, you subtract the initial point from the terminal point. So let's say just a quick visual description of that. Okay, so let's say our line segment is no longer at the origin to some point out there. Let's say it's from here to here. Okay, so that's our line segment. And we'll call this line segment P, this point P. We'll call this point Q. Well, this is our initial point. So this would just be the XY point. We'll call it P1 and P2. P sub 1, P sub 2. And this is our, we'll make that a lowercase q. Q sub 1 and Q sub 2. So this is our initial point, and this is our terminal point. Okay. Now our vector is going to equal the line segment, or the directed line segment, from our initial point to our terminal point Q. Okay. But remember, in order to find out what that vector is, we subtract our initial point from our terminal point. So that would be our terminal point minus our initial point. Okay. Now what if we decided instead we're going to switch those up and make this our terminal point and this our initial point? It's the exact same thing. You just have to make sure you know which one is your terminal point. So we'll make that vector W fits from, said, going from Q to P. Remember, your first one is always your initial point, and that's your terminal point. So here we're going from P to Q. That's our initial and our terminal. So it's going to be Q minus P. So Q1 minus P1, Q2 minus P2. With this one, since we're going from Q to P, it's going to be P1 minus Q1, and then P2 minus Q2. So it all depends on which one's your terminal point and which one's your initial point. All right, so even if you have some unidentified line segment, you can create a vector from it. Yes?
So how do you determine which one is initial and which one is terminal, since they both have a dollar?
Oh, because here it depends on which direction you're going for. So if you're going for the direction this way, then this is going to be your initial and this is going to be your terminal. And it'll always appear first for your initial. But if you're looking for the direction where you're going the opposite way, if you want to make this your initial and this one your terminal, then you're just kind of switching directions. Then in this case, your Q is the initial and your P is the terminal. So it all depends on direction. In this case, initial, and this is terminal. So that's really the only difference between just a regular ordinary line segment and a vector, is that with a vector, direction is really important. All right, any other questions on this one? All right. Looks like everyone got that. Okay, so let's do a quick example. Find the position vector of the line segment. Okay, so let's say we have our line segment. We have our X, we have our Y. Okay, and this is our line segment. Okay, so they go from 2, 5, bless you, to 3, negative 1. Okay. Now with this one, they don't tell you which one's the initial and which one's the terminal. You can tell by the arrow. Wherever the arrow is, that's your terminal. So sometimes it will say you have a terminal point here, but sometimes they'll give you just a graph and say, figure it out. You say, okay, I know just by the arrow that this is our terminal point. So when you have just the graph, be sure to look for the arrow. Okay, so we know that our position vector is going to equal a vector that has the terminal point minus the initial point. Okay, so that means we're going to have the vector where the point 3, 1, or 3, negative 1, minus the point 2, 5. Okay, so that means, actually that should be, yep, actually that's right there. So remember, you're subtracting vectors. So you're not subtracting it the way you would regular functions. So you have 3 minus 2 and negative 1 minus 5. Okay, so that means you have 1, negative 6. As your position vector. Okay. And what this means is that if you get that vector, because remember, vectors that have the same direction and magnitude, you can move them all over the place. If you get this vector, and you just get the whole thing and move it around and place this at the origin, the very tip of that vector will be right here. Does that make sense? Okay. All right, do one more example. Leave that up for a few more seconds. Make sure everybody got it. All right. So let's say if you want to know what is the position vector for the line segment okay, so let's say here X and Y, and let's say this one goes here, where this is your 1, negative 6, and this is negative 4, 1. Okay, so we know just by the arrow that this is our terminal point. Okay, so we can find our position vector the terminal point minus the initial point. Oh, actually, going back to the previous one, these actually should be the vector brackets. I think I was writing a little too fast. So it should be like that. Sorry about that. So as soon as you add or subtract two vector points, you end up with another vector. I didn't think about the fact that I did that until I rewrote it there. Okay. So that would equal your terminal point, which in this case is -4, -4, 1, minus your initial point, which in this case is 1, -6. Okay, so that gives us the vector -4 minus 1, and 1 minus -6. Okay, so that gives us -5 and 7. Okay, which is our position vector. All right, so any questions on that one? All right, now we've mentioned magnitude and direction over and over and over. Now we're going to figure out how to find the magnitude and direction of a vector. Okay, so the magnitude, which is just another way to say length, of a vector looks like the absolute value symbol. Okay, so that's just equal to the square root. And if you look at it, it looks like the Pythagorean theorem. So it's the square root of the first component squared plus the second component squared. Okay, so this doesn't mean absolute value. It just means the magnitude. So if you see that, you don't want to confuse it with the absolute value. So it does not mean absolute value. Okay. Now the direction of a vector we're going to use the same tangent inverse that we've used already. But that's the tangent inverse of the second component divided by the first component. And that tells us the direction just using theta. Now, when finding the direction, or your theta, the quadrant is very important. Uh-oh. when calculating your theta. Okay, so it all depends on which quadrant your vector is in. If your vector is in quadrant, let's say quadrant 3. No, I'm trying to think. Nope, if it's in quadrant 2, then you have your top and bottom will be negative. Let's say if it's -1. If it's -1 in quadrant 2, then you could have a vector of -2, 2. So your theta could be, say, 120 degrees. But that same theta could also be -2 here. So it all depends on which quadrant you're in to determine which theta you'd actually use. So this could be theta equals something, and this could be a different theta, or be negative something. Okay. Well, we'll actually cover that in the example. Oh, sorry about that. Thought I had it up further. Looks like everyone has it. Okay, so let's say, for example, let's say the vector for a line segment from P to Q has an initial point that we'll call P of 5, 6, and terminal point that we'll call Q at the point 9, 10. Okay, so find the magnitude and direction. Okay, so the one thing we know is that to find the magnitude and direction, we need the position vector. So we have our initial and terminal point, so the first thing we have to do is find our position vector. Okay, so we know our position vector is equal to our P and Q. Okay, and we know we can find that initial vector by the terminal point minus the initial point. Okay, so that's going to equal our terminal point, which is 9, 10, minus our initial point, which is 5, 6. Okay, so there I have 9 minus 5. And we have 10 minus 6. Okay, so that means our position vector is 4. Oh, actually 4, 4. I don't know why I was getting ready to put -4. Okay, so this is our position vector, V. Kind of separate that a little bit. Okay, so we can use that now to find our magnitude. Okay, so our magnitude of v. Remember that's the square root of your first component squared plus your second component squared. So that's just going to equal the square root of 4 squared plus your second component, which is also 4. Okay, which is square root of 16 plus 16. Okay, and that equals the square root of 32, which simplified is just 4 times square root of 2. So our magnitude is equal to 4 square root of 2. Okay, so now we find our direction. We'll bring that up a little bit. Okay, so if we find our direction, we know that our theta is equal to the tangent inverse of our second component divided by our first component. Okay, so that's tangent inverse. In this case, 4 divided by 4. Okay, so we know that our theta is equal to tangent inverse of 1. Okay, so if we apply tangent to both sides, then that will give us tangent of theta. The tangent and tangent inverse will cancel out there, would equal 1. We'll continue this up here. Now, the one thing you want to remember, that our position vector, that's in quadrant 1. So you measure that position vector the same way you would with a regular XY coordinate. Okay, so since our position vector is in quadrant 1, that means that our theta will be in quadrant 1 also. Okay, so tangent of theta equals 1 when theta is equal to 45 degrees. Okay, so that's your direction. Okay, so in the next example, it actually won't be in quadrant 1. All right, so any questions on that one? All right, leave that up for a few more seconds. All right. Okay, so let's say for our next example, if we're given that point P is at -3, -6, and point Q is at 7, -16, find the magnitude and direction of the